So like Liz said, I'm right across the street in CSAIL, where I'm advised by Tamara Broderick. So among other things, I'm really interested in Bayesian robustness, which sort of broadly is the study of what happens when you accept the fact that whenever you write down a Bayesian model or any statistical model, there are always just huge simplifications of reality that you made, and so you should be aware of that. So in particular, why this is relevant to think about is because statistical models are becoming more and more commonly used in sciences to make inferences about the real world. I think that's maybe not surprising, especially to people in this room. So, like in particle physics, Bayesian models actually are very commonly used to make various inferences about whether particles exist or not. An example more in the biological space is the fine mapping problem, where you're trying to decide, what genes are important for a particular trait. But in order to make these inferences, you have to write down a model. And when you write down this model, you have to make a ton of simplifications about the world. And the reason why this is super important is because we're going to take these simplifications and then use them to make claims about the real world, like which genes are important for characteristics such as cancer. And so if we want to actually have our claims be accurate, we have to really understand how our particular simplifications influenced our inferences. And in particular, if there's some heavy influence here, we'd say that we're not very robust. Okay, so let me kind of immediately be a little bit more specific about what I mean by what is a statistical model and what do I mean by simplification. Let me do that by sort of stepping through the process of how we might construct a Bayesian model or a statistical model in general. So the first thing we start with in any modeling problem is we've got some data. My data set's going to be capital X with data points x1 through x capital N. And so just going back to our fine mapping problem before, where our data is going to be pairs, actually, yn comma zn, where y is going to be, say, a person's height, just for simplicity. And then zn is going to be this big d-dimensional vector, which is going to be maybe some region of a person's genome. And what we're interested in is how that region of the genome, which genes in it, affect their person's height. Okay, now in order to get that information out of our data, we're going to posit the existence of some parameter, theta star. Theta star is going to be an element of some set, capital theta, which is like our set of valid parameters. You can just think of that as like all possible real numbers for the purpose of this talk. And we're going to say that that theta star generated the data. So again, just going back to the fine mapping example, we might have that theta star is a d-dimensional vector, where the dth component of it is the effect of the dth gene on height. Okay, now these parameters are kind of useless in a vacuum. In order to make them useful, we have to answer the question of how do we think that theta star generated the data? And typically in a Bayesian model, or in many statistical models in general, we'll say that the data were drawn from some likelihood, p of x given theta star. It's going to be a probability distribution over the data. Again, in the fine mapping example, a common thing to do is assume a linear regression model, where we say that heights are drawn from a normal distribution for each individual, where each individual's normal distribution is centered around some linear combination of this particular region of the genome that we're interested in. And the weights, of course, are going to be theta star. Okay, now this is all just like a very generic setup just in any time we're doing statistical modeling. If you're going to do some kind of maximum likelihood estimate with some frequentist model, there's still going to be data, there's still going to be parameters, and there's still going to be a likelihood. What's really specific to Bayesian analyses is that we also have a final ingredient, which is the existence of some prior beliefs about theta star. And those are going to come in the form of some prior distribution pi naught over theta. There's going to be a probability distribution that tells us, or not tells us, that we write down which values of theta star we think are more likely to be true. So just to finish off our example, maybe we think that small values of theta star here are more likely because we expect that individual genes will typically have like very small effects on height. And so maybe we'll write down our prior beliefs are that theta star follows a zero mean normal distribution. Okay, now we take all of these ingredients and we form the posterior, which encodes our beliefs about theta after having observed the data x. And this posterior we can compute using Bayes' rule, where this posterior is going to be a distribution pi of theta conditioned on x, and Bayes' rule just tells us that it's proportional to our likelihood times our prior. Okay, so that's kind of the traditional map of like how you come up with a model. Now, why should we be concerned about robustness? Where does robustness enter into this recipe? Now remember, there were two things that went into our posterior, right? There was the likelihood, which encoded how theta star generated our observed data, and then we had our prior, which encoded our prior beliefs about theta star. And just to really quickly recap, we said for our likelihood, we were going to do a linear regression model, and our prior, we thought smaller values of theta were more likely, so we use a zero mean normal distribution. Now, these are both huge simplifications of reality, right? I mean, we wrote these down in such simple forms, mostly for mathematical and computational convenience. It's kind of just us being a little lazy, I guess. And the fact is there are lots of other valid simplifications, right? I mean, why does this have to be a normal distribution? There's no real biological reason to think that's a normal distribution versus considering something that was maybe slightly heavier tailed than a normal distribution there. Right? I mean, there are lots of other ways we could change this model that would also be valid. This just happens to be one example. And since if you sort of told me, hey, Will, would you prefer, do you think it's more biologically realistic to use a normal distribution here, or it's a distribution that's just slightly heavier tailed? I would say, I presume most people here would agree, that there's no real reason to prefer, biological reason to prefer one over the other. And since there's no reason to prefer one or the other, it better be that our inferences are stable as we sort of swap one out. In particular, if the posterior depends really heavy on the particular simplification, on having used a normal versus something slightly heavier tailed than a normal, then we're in big trouble. We can't really trust our inferences. And so we want to study what exactly happens to the posterior when we make reasonable changes to the model. Yeah?
Are you considering robustness also in terms of, well, maybe linear additive model is not reasonable?
Yeah, exactly. Yeah, so that's totally another reasonable change that you might make to this model. There's tons and tons of reasonable changes, and that's actually something that's really difficult. I'll touch on that a little bit about prior robustness, but it's true in general, is considering what the class of like reasonable changes to your model are that you would also just believe in as well. That's a really difficult thing to do, and then you kind of want to take the maximal change over that set. That's sort of the idea behind robustness in general. Okay, so let me just give you the very brief 3-point overview of what I'm going to talk about for the rest of the time. First, I just want to clear up that I'm talking about modeling robustness and not adversarial robustness. And then we'll get into the Bayesian side of things immediately and start talking about the first kind of Bayesian robustness, which is prior robustness. And then we'll close up by just talking about what happens when you've misspecified the likelihood, how robustness issues can crop up in that case. Okay, so let's start right away on this first issue. So I just want to bring this up just because robustness is a really popular term these days, something you might hear around a lot. I want to clarify exactly what kind of robustness I'm talking about. That's because broadly, I think there are two categories of robustness that you might see. The first, people will call adversarial robustness. You'll see this a lot in like the deep learning literature. The concern here is that an adversary is going to mess with your data. For example, what people are concerned about is that I'm going to train a neural network to drive a car, and maybe somebody is like poisoned my training set in order to make me crash, or someone's like out on the road and is, put pieces of tape on a stop sign to convert it into a speed limit 55 sign, and it's going to make my car speed through it. These are real things that happen, particularly the messing with the car on the road. Like there are literally examples of this happening. So that's a very concerning thing. The second type of robustness is modeling robustness. And that's just the fact that the modeling assumptions we wrote down are not a perfect reflection of reality. And that's what I've been talking about in the last few slides, right, is only modeling robustness. And the reason that I focused on that is because I think it's a little bit more relevant to the scientific context. I mean, unless maybe the broad is like more cutthroat than I'm assuming, and you have like rival scientists sneaking into your lab at night and like messing with your lab notebook in order to like give you the wrong conclusions. But I'd like to believe that's not happening here. So we're only going to talk about modeling robustness of Bayesian inference here. Okay, so let's immediately just get into talking about prior robustness here. So just to recall, our posterior is composed of two parts. We're going to go over each part in turn, and we're just starting with robustness to the specification of the prior. And the question we really want to tackle is, if I wrote down different prior assumptions, pi naught, how would the posterior change? Now, this is a pretty large focus of Bayesian robustness in the 1990s. I have to admit, I was not an active researcher in the Bayesian field in the 1990s. I wasn't an active researcher in anything at the time. I was, in like elementary school. But my understanding is that this major focus kind of started in part due to criticisms of Bayesian's use of priors. Right? So like the big criticism of Bayesianism from the frequentist community was, well, yeah, it's cool that you've made all these neat inferences about the real world, but to do that, you had to make up this prior. And the prior is this subjective thing that varies from person to person. So like, don't your inferences about the real world also vary from person to person? And so isn't Bayesian statistics really stupid? And so my understanding again is that the response was, well, fine. We will make an explicit study of how our inferences about the real world depended on our prior assumptions. And so that's sort of what I'm going to go over today. Well, in part today. Okay, so in order to really make a study of this, we need to specify what are reasonable changes to the prior. What are other valid priors that we should be considering and that we want to be robust to? And in order to do this, I think it's instructive to think about what prior beliefs typically look like. In particular, they're usually not of the form, I believe that theta follows a multivariate Gaussian with mean 0 and covariant sigma. Now, in truth, this is what you will see written down in papers, and this is what will be implemented in computer code. But I'm pretty confident that there is no scientist who truly believes that a physically meaningful parameter theta actually follows a Gaussian distribution. That's just a simplified representation of someone's prior beliefs. Instead, what prior beliefs actually look like in practice might be something that's maybe just a bulleted list with a few qualitative high-level descriptions about what you believe about theta. So for example, maybe I know that theta has some physical meaning, and because of that physical meaning, I know that it cannot have magnitude bigger than 1.6. It's physically impossible for it to be outside the realm of negative 1.6 to positive 1.6. And maybe in addition to that, the consensus in the scientific community about this magical parameter theta is that smaller values of theta are just more likely to come up. And okay, these are the two pieces of prior information that I've gathered as a statistician. And I say, oh, okay, I can model that. I'll use a truncated Gaussian distribution. In particular, something like this, right? So great, it's 0 outside the range, plus minus 1.6, and smaller values are more likely. That seems like a valid representation of these two prior beliefs. The issue is that another person with the same exact two prior beliefs also might write down a different prior, like this orange one. It is also 0 outside plus minus 1.6, and it also has smaller values of theta being more likely. So who's to say that either one of these is more valid than the other? Both of them totally align with our prior beliefs. And so our big fear here is, will writing down this different prior change our inferences a lot? And if it is, we'd say that we're very non-robust to the choice of the prior. because there's no reason that a reasonable person would prefer the orange one to the blue one. Okay, so I just want to get a little bit notation down to be a little bit more qualitative about this. So again, what we did was we wrote down some prior pi naught. And then we're going to have to specify some other set of reasonable priors. All these alternative priors I'm going to denote by pi tilde sub 0. And they're going to lie in some set B centered around pi 0. That's going to be our set of alternative reasonable priors. And so just to call back to the example in the previous slide, the blue thing was the truncated Gaussian, the pi 0 that we wrote down to begin with. And then the orange thing was an alternative pi tilde that lies in this set B. So what we're often interested in Bayesian statistics is we're interested in posterior expectations when our prior was pi naught. So it'll be of this form. So right, it's an expectation with respect to the posterior distribution, and the thing we're taking the expectation of is some function f of theta. Where so, for example, if f of theta is equal to theta, then we're getting the mean of the posterior distribution. And notice I put a superscript on the expectation here. That's just to indicate which prior I use to form the posterior. That'll be useful in a minute when we're swapping out the different priors. And we'll say that we're robust to the choice of the prior if this thing is basically the same as the max over all the different priors that we think are reasonable. In particular, the max over all different alternative priors, pi tilde, in our reasonable set. And we're taking the max of the expectation, the posterior expectation of f, when we've swapped out the prior for a different pi tilde. Okay, so this leaves us with two questions here. One, what is the reasonable set B of pi? And two, how do we compute this maximum? So I'm going to answer both of these questions in turn. And I'll start with how should we think about computing this or picking this set of other reasonable priors. Now picking the set of other reasonable priors is incredibly problem dependent because it totally depends on what your prior beliefs are and what the problem is. So I can't give any like general purpose advice, but what I can do is just give a cautionary story about why you need to be really careful about specifying this set, because otherwise you might be way overly pessimistic and you might come to the conclusion that Bayesian inference is completely useless. So I'm going to do this by telling you about a result from Owaldi et al. In 2015. It's a really interesting result about prior robustness. And what they do is they take the set of other reasonable priors to be the total variation ball of size epsilon. Now I'll just tell you, total variation it's a metric on probability distributions. It's not super important what it looks like. I'm not going to write it down, but let me just draw two things that are in a total variation ball. They're very close in total variation distance, just so we can get a feel of what it looks like. So let's say there are two experts, Alice and Bob. Alice writes down our prior pi naught, which is our truncated Gaussian from before. And now Bob is going to write down an equivalent reasonable prior that is of small total variation distance from Alice's prior. And here's what Bob's prior looks like. Okay, now the total variation distance permits sort of a lot of things. It's a very strong metric. And so despite the fact that there's this like weird cutout, it is true if you look at the form of the total variation metric, these are within a small TV distance of one another. So if this is our set B epsilon, is our total variation ball, then Bob's prior is in the set B. Okay, and so now Owaldi et al. Have the following interesting result, which is that under some mild technical conditions, which are not crazy, like real problems satisfy these conditions, Bayesian inference is infinitely non-robust to the choice of the prior. And when I say infinitely non-robust, what I mean is this, that the max over all possible alternative priors of the posterior expectation is in fact equal to the maximal value that the posterior expectation can take on, right? So if our set of valid parameters theta is like the real line, and we're just taking the mean, so that f of theta equals theta, then for any small total variation ball around our initial prior pi naught, we can make the posterior mean equal to infinity. So things can like go totally off the rails when we take this max over this total variation ball. Okay, now the reason why I don't think that Bayesian inference is completely useless based on this result is because I don't think that these are reasonable priors to switch between, right? I mean, if Alice and Bob are two experts about this problem, and they each went into their offices and wrote down priors corresponding to their beliefs, and Alice came out with this one, and Bob came out with this one, Alice is going to be like, whoa, Bob, like, what do you know about the value of theta around 0 that I do not? Right? Bob's prior information is clearly different from Alice's in this problem. And so it's kind of actually a good thing that Bayesian inference has this kind of sensitivity, because what it's saying is, if you put in completely different prior beliefs, what comes out are completely different posterior inferences. So this is just to say, you need to be very careful about what you're considering an alternative reasonable prior. Otherwise, you might be very pessimistic about how well you're doing and about how sensitive Bayesian inference is. Yeah?
What's the intuition for what choice of pi naught tilde gives you this maximum?
So it's this picture. So it's a very data, so the worst case prior is going to be dependent on the data that you've observed. And it's something like, if you observe a point at 0.0, then the sort of limiting, actually this should be a soup, but sort of like the limiting thing is an exact cutout that places 0 prior mass there. And then like the data was telling you that it should be there, and then suddenly it's saying that it can't be there under our worst case prior. It's actually interesting. Their like proof tells you that this is kind of the worst case prior.
That's in the parameter space, not the data space.
Yeah, so this is with a particular likelihood. And I'm kind of forgetting what the likelihood is right now, but it's under something that would like very strongly tell you that the value of the parameter should be here, like given the data that you observe, and then this completely throws everything off. So actually, so Waldy et al., this paper is not the one that has the original result. This is just like a survey paper of a few of the results. It's a really interesting paper. I can point you to the reference if you're interested. But okay, in any case, this is just sort of the example of why you got to be careful about choosing this ball. Now I want to briefly talk about, let's say that we've somehow specified this ball to a satisfactory degree of alternative priors. Now we have to compute this max somehow. And the reason why this should be concerning is because Bayesian inference for just a single prior is often really hard. Right? You have to run MCMC, you have to, MCMC can be slow, and then you've got to deal with has it mixed or not. There's autocorrelation among the samples, and there's just all these sorts of different issues. And now we're allegedly going to solve a maximum over a huge set of alternative priors, possibly infinite set. We're somehow going to optimize over that. That seems like completely ridiculous. Okay, so one case in which we can actually do something is when our pi 0, the prior we wrote down, depends on some hyperparameters alpha, which is a pretty common situation. What I mean by hyperparameters is say that we've written down our pi 0 is some 0 mean normal distribution, and the variance is a quarter. Like this is just what we've written down as our prior beliefs. In this case, our hyperparameters are 0 and a quarter. It's just these two numbers. Okay, well, it's not too crazy to think that maybe in this case, we want our set of alternative reasonable priors to encode different choices of hyperparameters. For example, are my prior beliefs really expressed by the variance being a quarter and not 0.3? Doesn't seem like there's too many problems in which you're like, oh yeah, a variance of a quarter really nails down my prior beliefs and not 0.3. So you might want to consider switching between those two. In particular, we might want to consider switching between computing both of these posterior expectations. Where here I've changed up the notation just slightly, just to make things a little bit easier on the next slide. Whereas the superscript that I've written here just indicates the different hyperparameters that I'm using in my prior. Okay, and what we can do in this case is it's still incredibly difficult to exactly compute this maximum, but we can actually approximate the max pretty well by taking some derivatives. And the key idea is that it turns out you can differentiate posterior expectations with respect to the hyperparameters alpha. I'm not going to go into the exact details of how you do that, but it's actually not super difficult. And so then, given these derivatives, what we can do is we can approximate the max, or we can approximate the objective of the max in particular, by a first-order Taylor series around alpha 0. So what I mean by this, there's just a bunch of notation, and it's kind of obscuring a really simple idea here. What I mean is that, say we're interested in the posterior expectation when our hyperparameters are some alpha 0 plus some change in alpha. And we'll just approximate that by a first-order Taylor series around alpha 0. So the 0th order term is just going to be the hyperparameters are alpha 0. And we'll add on this linear term where we have the derivative of a posterior expectation with respect to alpha, and then times our change in alpha. It's literally just a first-order Taylor series in alpha. Okay, and then what implementing this idea in practice might look like, this is a figure that I've lifted from a paper where they're doing something almost exactly the same. It looks like this in practice. So on the x-axis here, I've plotted the change in alpha, and now on the vertical axis, I've plotted what the change in the posterior expectation is. So this guy minus this guy. Now the red line here is showing if we recompute this change exactly. So for each red dot here, we had to rerun Bayesian inference. We had to rerun MCMC. This approximation, on the other hand, is the blue line, and it makes sense that it's just this like linear thing. It's just a straight line because the function we're plotting is this thing, which is linear in the change in alpha. And the approximation is not perfect. I don't want anybody to think that like, wow, this just crushes your problem entirely and completely. As the change in alpha gets bigger and bigger, the approximation does degrade, and you can imagine that if this went much further to the side, we would get like some real divergence here. But for moderate settings of alpha, it's not too bad. Now the reason why this is so awesome is because I didn't tell you how you can compute these derivatives, but I will just assert that in fact you can compute them using posterior samples under our original prior, when the hyperparameters were alpha 0. And importantly, you were going to take these samples anyway, just to do Bayesian inference. Right? So the expectation that you were interested in the first place is this guy, and you're going to take some samples from the posterior in order to estimate that expectation. Well, those same samples can be used to compute this derivative, is what I'm saying. So to compute this entire blue line, we only had to run MCMC once, whereas to compute this red line, there are like, 20 red dots on here, we had to run MCMC 20 times. So huge computational savings. So what I really want you to take away here is that this is a very practical thing that you can do anytime that you have hyperparameters in your Bayesian model. Okay, so that kind of wraps up what I wanted to say about prior robustness. Let's move on to talk about what happens in model misspecification. And just to recall, we just talked about the prior, which is 1/2 of the posterior. Now we're going to be talking about the likelihood, and in particular, what happens when the likelihood is misspecified. So we're going to explore the question of what happens to my posterior when my data xn are not drawn from some true likelihood p of x given theta star, where theta star is any of our model parameters. And in this case, we'll say that we have model misspecification. The likelihood has not been correctly specified. And again, we need to specify what reasonable misspecification looks like. That's sort of what our example before was telling us, that we've got to be careful about what we're considering to be reasonable levels of misspecification. Now in this case, there's almost always some misspecification. And sometimes there's a really significantly large amount of misspecification. Like, for example, do we really believe that the way that a region of my genome has constructed my height was by taking a linear combination of that region of the genome and then adding normal's noise to it? I mean, I wasn't there when my height was being selected, but I'm pretty confident that that's not how it was done. And so we want to be robust to changes like this. Right, so like, can my height be negative? Okay, and I'm going to illustrate what can happen to a posterior when your likelihood is misspecified by just talking through a particular example. An example of a really simple model, it's very commonly used, just linear regression. So the example that I'm going to be talking through is from a paper by Grunwald and Van Omen in 2017. And they generate a data set where there are pairs of points. On the horizontal axis here, I'm going to call them ZNs, and on the vertical axis, I'm going to call them YNs. And the goal is going to be a standard regression setup. The goal is to predict YN given ZN. Now, before I go into exactly how we're going to do that, let me just tell you about how the data was generated so you don't think that it's like some crazy data set. So we're generating these pairs ZN and YN. They're both real valued. And we're going to flip a coin, and with probability half, if it lands on heads, we're just going to set both ZN and YN to be 0, 0. So that's actually why I've drawn like a big bolded point here at the origin, is because roughly half of the data set is actually just like stacked up there. Now, if our coin lands up tails, then instead, we're just going to draw ZN uniformly along here. And then for YN, we're just going to do some normal random noise. So they're going to be completely unrelated. So it's not too hard to see that if we had to pick basically any relationship between YN and ZN, and we wanted to predict future data using that relationship, the best thing that we can do is just this red line, right? Is just to always predict ZN is a half, what should my YN be? Predict 0. ZN is a quarter, what should YN be? Predict 0. This is going to give us the best predictions in the future. And so we might kind of hope that that's what will happen with Bayesian inference. But let's say that we don't actually know that this is the best fit line. And so instead, what we decide to do is say, well, maybe there's some polynomial relationship between YN and ZN. And so what we'll do is do linear regression using polynomial features. In particular, we'll set our covariates to be 1, comma ZN squared, comma ZN cubed, all the way up to ZN to the dth power. And then we'll do a standard Bayesian linear regression setup here. Or then we're going to say, YN is drawn from normal distribution centered at our covariates summed up with these betas, which are going to be our regression coefficients as the weights. And we'll put a prior on beta, and we'll put a prior on our noise here, sigma, but those aren't super important. What is important is that we're also going to assume we don't know what the degree of this polynomial is. We don't know what d is. So we'll put a prior on d as well. Okay, and what's relevant about this prior is that it's monotonically decreasing with d. So d equals 0, which is the simplest possible model. So that red line I had drawn before was an example of d equals 0. There's no dependence, it's a constant function. D equals 0 is the thing that we're saying we believe in the most. And then as the models get more and more complicated, as d grows, we're saying we believe in them less and less. Now, I say there's misspecification in this case because y conditioned on our covariates, or rather y conditioned on z, is not in our model class. But it's only barely not in our model class, right? So the thing that we've assumed by writing down this distribution, this likelihood for YN, is we've assumed that the noise here, this sigma, is independent of Zn. But in fact, it's not. Right? Because right here at Zn equals 0, there's no noise. Because at Zn equals 0, Yn is always 0, so the noise is 0. And then elsewhere throughout this interval, there is some noise. So it was drawn from a normal 0, half distribution. And so we'd say that the problem here is that there's heteroscedasticity in our data, which literally just means that the noise is not constant. That's all heteroscedasticity means. Okay, and so, but we might hope that Bayes is still going to do something reasonable here. And yet, this basic level of misspecification will completely break Bayesian inference. So just to reiterate, again, the best model is d equals 0. And that's the thing we put the highest probability mass on. It's this red line. So we can ask ourselves what will happen as we get more and more data, as I put more blue dots on this picture. We might hope that the posterior would be like, oh yeah, I'm really sure now this red line is the right thing. But in fact, Grunwald and Van Omen show empirically through some experiments that the posterior seems to concentrate on d equals infinity. So as I observe more and more data, the posterior will prefer more and more complex models. It'll just go on to like crazy, squiggly things like this, just higher and higher degree polynomials. This seems extremely undesirable because, one, just at like a qualitative level, this doesn't describe the data very well, right? Say like, hey, what's the trend between Zn and Yn? And you're like, well, the posterior tells me it's some crazy squiggly thing, versus, oh, it's this nice simple red line. So it's poor qualitative description of the data. And furthermore, in terms of predicting the data well, it's going to do terrible, right? If I give you some more randomly sampled data points from there and tell you to predict them using the red line, you'll do all right. If you try and predict them using this squiggly blue line, you're going to do disastrously poorly. Yeah?
Is there a difference between the posterior max and mean in this case?
Oh, that's a good question. So yes, so what I'm plotting is it's a fact about the map, the sort of maximal value of it. I actually don't know if this holds for the mean as well. That's a good point. Yeah. Okay, but this seems sort of disastrous. So certainly disastrous if what we want to pick is the highest probability model in our posterior, maybe the mean as well. And so can we recover at all? Like, is Bayesian inference just totally busted? Well, one way of dealing with this kind of misspecification is an area that's been getting some recent interest, which is studying power posteriors. So just recall the regular posterior, it's just the likelihood times the prior. A power posterior is a really, really, really simple modification where all you've done, we've taken the likelihood, but we've raised it to an exponent eta, where eta is going to be some number bigger than 0. Oftentimes, you might intuitively think that using eta less than 1, and oftentimes you do use eta less than 1, is just sort of a way of down-weighting the untrustworthy likelihood, because the likelihood is misspecified, so maybe we don't like it as much. I will say, I said this is somewhat of a popular recent area. There are lots of different ways of interpreting what eta is, and also different ways of picking it. So Peter Grunwald, who's one of the authors on that paper that had that linear regression example I was just showing, in 2012 he has this paper where he calls this, he has a paper where he proposed an algorithm that he calls safe Bayes. It's a particular way for picking what eta is. And in the later paper that has this linear regression example that totally breaks regular Bayesian inference, they show that their safe Bayesian procedure, which uses a power posterior, is not defeated by that example. So in that case, the power posterior does the right thing and does not just like drift off to d equals infinity. Another example is from Jeff Miller and David Dunson, who proposed something called a coarsened posterior, which basically, instead of conditioning on the actual data just being like the true data, assume that there's some nearby true data, and they want to condition on that fact. And they end up showing that a power posterior approximates this coarsened posterior pretty well. And in fact, they have some really interesting examples of what can go wrong with regular Bayesian inference in their paper, when there's misspecification, and they show that their particular power posterior that they use totally defeats those examples as well, that it does sort of the right thing. And then finally, in a slightly different way of using power posterior, we'll have Jonathan's work, where he'll talk about something that he calls a bagged posterior, where instead of attaching a single weight to the entire likelihood, oftentimes the likelihood is broken up into many different terms, and he'll attach a different weight to each one. And I will say, just as like a piece of practical advice, it seems that really using any eta less than 1 is helpful in both practice and theory. So, if you have the opportunity and you're doing some Bayesian inference, maybe just, pick eta equals 0.8 or something. This can make inference a little bit harder, so don't go crazy. But, I really wanted to highlight this slide, though, because it seems like a really, really interesting area of research. And, I think it's an area of Bayesian research to watch out for in the next few years.
Question?
Yeah.
For the eta, can you think of in an intuitive sense, how much to trust your likelihood, basically? Is
Yeah.
that kind of like the...
Yeah, I think that's definitely one interpretation of it, because it definitely, it downweights the likelihood with respect to your prior. So, yeah.
So could you formalize the trade-off between power and robustness in any meaningful way in simple examples?
Yeah. I mean, so I know in Jeff Miller's work, the eta that they end up picking is roughly proportional to 1 divided by n, where n is the amount of data. You can correct me if I'm saying something wrong here, but and so their posterior won't actually fully concentrate on anything as n goes to infinity. But it also definitely won't concentrate on crazy things, so that's good. So its maximum will stay at something reasonable, in fact. It'll stay, they don't actually do this linear regression example, but in corresponding examples, basically its maximum, its map would have been on d equals 0. But even at n equals infinity, it wouldn't have given a probability 1 spike at d equals 0. It would have left some mass elsewhere.
Yeah, I'll say one other thing, which is, Peter Grunwald's work, they focus on the case where essentially there's some critical eta value, and then once you're sort of below that critical value, and where that value depends on sort of how misspecified the model is, everything becomes well behaved. And so they're basically, their safe Bayes algorithm is trying to figure out where that critical eta value is. So that's some really nice work. And they're sort of there's a very nice geometric intuition in terms of specifying your model space.
And it's a constant threshold, or it depends on n?
The threshold depends on the model and how the data is generated. It doesn't depend on n. It's independent of n.
Right. Okay, so just got out of time, so let me just wrap up briefly. What we said is, our models are always approximations, so you should always have robustness on your mind. We talked a little bit about Bayesian prior robustness, where the issue was, yes, we wrote down a prior, but lots of other reasonable priors exist out there. And we need to be very careful about what a reasonable prior is. What's a reasonable alternative prior. And then we went through briefly the fact that there are these really practical robustness measures that you can compute, and they're very easy to compute. It's an approximation to the robustness thing we care about, and they're only really available when you're considering robustness to hyperparameters, but they're super easy to do. Then we talked a little bit about likelihood misspecification and what can go wrong there. In particular, this is pretty innocuous looking misspecification in linear regression just totally threw things off the rails. And then we saw that power posteriors can maybe present a way forward from this problem. Okay, that's all I have, so thanks.
Hi everyone, thanks for coming. Yeah, so got a really nice introduction to some of the issues around robustness from Will, and I'm going to be focusing on the misspecification aspect, so when our likelihood is wrong. And I'll be talking about a very simple procedure
for modifying standard Bayesian inference to make it more robust, and basically combining it with a sort of very classical frequentist method, which is the bootstrap. Okay, so I want to start out with a motivating example. And the example in this case is nothing, so we're not curing cancer or anything quite that amazing. We're just trying to predict the future insurance claims for this insurer based on some historic data that they have, okay? And what we might try to do, if we're Bayesian, is write down a model. So this model I didn't actually come up with. It's sort of based on standard actuarial techniques. And so you write down this model. It's pretty non-trivial. It involves these 10 time series. And you crank through it, and you get this posterior distribution over sort of this future amount of money that this insurer might have to pay out based on the plans that they've written, okay? And so this is great. We like Bayesian inference because it sort of quantifies our uncertainty about what the claims might be. And so we sort of say, okay, well, it looks like maybe somewhere between $60,000 and $75,000. All right. So then we'd be pretty disappointed to find out that, in fact, the true amount of future claims that we paid out in this case was actually significantly less than what our posterior said was plausible, right? So the true payout was more like $50,000, right? And as an insurer, you sort of decide how much money to kind of have around so that you can pay out these claims, and you would have just kept way too much around and basically lost money in this case. But if it turned out that the true claim was up here, then you wouldn't have had enough. That would have been maybe even worse. So the problem here is that our uncertainty is not well calibrated. And this is another example of sort of what can happen when a model is misspecified. That when we use Bayesian inference and the model is misspecified, we have no guarantee that our uncertainty is going to be well calibrated. And that can lead us to make bad decisions. Okay. So another thing you might try if you're not Bayesian is you might try to use the bootstrap. Okay? And this is the bootstrap distribution that you'd get. So this part here kind of looks a lot like the standard posterior, but then you have this big spike down here, okay? And I guess in some ways this is better because it seems to be acknowledging the fact that the future claims amount might be significantly less. But apparently there's no chance of it being between about 12,000 and 52,000. So that seems a little crazy, right? So this isn't particularly satisfying either, and also wouldn't lead to particularly good decision making, I think. So what can we do? Well, we can basically combine Bayesian inference with the bootstrap, and we get this much more reasonable looking posterior. And as you can see, again, it sort of looks like the bootstrap here, but now we have this nice smooth tail. It's acknowledging the plausibility of getting these smaller future claims amounts. And so now if we kind of look at sort of like sort of credible interval, that's going to contain 95% credible interval or something, that's going to contain this true amount.
Does it get the spike in the bottom?
No, there's no spike from the bag posterior. Yeah, it doesn't have this weird spike. Okay. So that's sort of what we might be able to get from using this bag posterior or BayesBag. So in this talk, I want to first tell you exactly what BayesBag is, and focusing in on this parameter, inference, and prediction typesetting, like in the insurance example. Then I'll describe a little bit of BayesBag theory at a very high level and get into some of the methodology that we developed for how to actually make BayesBag practical. And then I'll conclude by talking about using BayesBag for model selection. And that's where I'll actually get into a fun, more biological example involving phylogenetic inference. Okay, so just to fix some notation, I know we've sort of been through this in the previous talk, but if you weren't there, so we're interested in Bayesian inference here, where our goal is to learn about some unobserved phenomenon. This is our parameter of interest, such as this future claims amount. We may have some prior beliefs about what are plausible values for this parameter, and we can encode those prior beliefs in this distribution pi naught. And then we get to observe some data that we think is affected by this, parameter that we can't see. And then we have this measurement model, P of y given theta. And when we view y as fixed, this is called our likelihood. And then we combine the prior and the likelihood to form the posterior distribution, which is now our updated beliefs about theta now that we've observed this data. Okay, so why do we like Bayesian inference? Well, it gives us these nice coherent belief updates. We automatically get uncertainty quantification. Modeling is very flexible because we can basically write down any prior and any model, and in principle, we know exactly what to do to get a posterior distribution. Of course, there are computational challenges, but it gives us a lot of modeling flexibility, which is really great. We can sort of do very problem-specific things. But there are a couple really important assumptions that are baked into Bayesian inference, at least on the statistical side. So one is that this measurement model is correct. And we've already seen in Will's talk some of the things that can go wrong. And in this insurance example, we saw another example of something that can go wrong when the assumed measurement model is not actually correct, right? That our assumption that the observed data was actually generated from P of y given theta true for some theta. And then there's a second, more subtle assumption, which is more about what happens when which is more relevant because we always have finite amounts of data, right? And when we have finite amounts of data, the prior is obviously going to have some effect on our inferences, right? And so if our prior doesn't put basically any mass on this sort of true parameter, then it doesn't even matter that theta true is in the model, right? If I sort of relative to the amount of data I have, I put extremely little mass on this theta, then it might as well just not be part of the parameter, part of the model. Okay. Okay. So that's Bayesian inference. So as I said, we're going to combine Bayesian inference with the bootstrap. So what is the bootstrap? So the bootstrap comes at things from a slightly different perspective, from a more frequentist perspective, where we imagine we have some distribution P sub true that's generating our data. Okay. In other words, we imagine that we have our data y1 through yn, and each observation yi is coming from this distribution P true. So here's some possible data that we might have gotten. Okay. Just sort of indicating where they are with these little lines. And what we're interested in doing, right, is finding the parameter that best explains this distribution. So a simple example might be maybe we just want to fit the mean of independent normal observations, right? Obviously, this distribution, it's not normal, but we could still try to find sort of the mean of the distribution by, say, assuming that the data is normal. Okay? But if we're coming at things from this frequentist perspective, what we're worried about is we only have a finite amount of data, right? And so we're worried basically about the sampling uncertainty that arises from the fact that if we had an infinite amount of data, we could nail down the mean exactly. But since we only have a finite amount of data, if we look at the mean that we get from, say, 7 observations, there's going to be some variability. So here's the distribution of the mean of these sort of small number of observations. Okay, and we'd like to sort of quantify that uncertainty that we have. And so what the bootstrap does is, well, okay, so what I should say is, in this example, I can just keep drawing data sets of size 7 or 8, and I can form this nice distribution, right? But in reality, I only get to observe one data set, okay? And so I can't just keep drawing new data sets from P sub true, okay? I only have my one data set. So what am I going to do? Well, the idea with the bootstrap is, okay, we can't keep sampling from P sub true, but what we can sample from is what I'll call P sub n, which is just the empirical distribution, okay? I just put a delta mass at the location of each of my observations. And so what I can do then is just redraw with replacement samples from Y. So yeah, sorry, we're looking at this bootstrap distribution and this bootstrap data set. And what we can see is, we've gotten this one observation now 3 times, this one twice, some not at all, okay? And we can sample a bunch of these bootstrap distribution or data sets, say 1 through B, and then we can make a histogram, and we'll get something like this, okay? And so it's not going to be centered in the right place because the empirical mean is not equal to the actual mean. But you can see it sort of gives us the right spread. And so this can be a good way to sort of understand what our sampling variability is. Okay, so what are the benefits of this bootstrapping approach? Well, we're not making any assumptions about how our data was generated, right? We saw for Bayesian inference, we're making these very strong assumptions that the likelihood model we wrote down is correct. Here, we're, say, assuming a normal model, which is clearly incorrect, but despite that, we can still sort of get this reasonable measure of our uncertainty about, say, the mean of the distribution. Another nice thing is it's very easy to use. You just kind of keep drawing these data sets and then computing means, or if you're doing something more complicated, maybe a maximum likelihood estimate for each of these bootstrap data sets. But in any case, it's pretty easy to do. And you can parallelize across B. So computing each of these, you can do just in parallel, right? They don't depend on each other. The challenges with the bootstrap are that B needs to be large usually to sort of get this full distribution, right? You need to take 1,000, 10,000, 100,000 samples. And so okay, maybe if this is computing a mean, that's easy. But if I'm, say, computing a maximum likelihood estimate and I have to solve some optimization problem, this could be very slow, especially if I have to do it 100,000 times. And also, finite sample properties of the bootstrap can be kind of suspect. And we saw that in this insurance example where you got that sort of wonky spike and then nothing in between where the rest of the mass was. Okay. So what are we going to do? Well, we're basically just going to combine the bootstrap with Bayesian inference and try to get the best of both worlds. So recall that I wrote that the posterior given data y is denoted as pi of theta given y. And if we have that, so here's what we might get for the uncertainty about this mean if we were to compute the standard posterior. Okay. And the idea with BayesBag is what we're going to do is we're going to, again, sample these bootstrap data sets. And then we're going to compute the posterior conditioned on each bootstrap data set. And then we're just going to average over these posteriors. Okay? And in that case, you might get something that looks like this orange distribution here. Okay? You can see it's sort of wider because we have essentially this additional uncertainty that's coming from resampling our data. So what we'll see is that by using this sort of bootstrapping of Bayes approach, we get some of the same benefits as the bootstrap, where we're no longer going to need this correct model assumption like we did with standard Bayes. It's going to be easy to use in the sense that if I knew how to compute my standard posterior, I'm just going to do the same thing a bunch of times. Will mentioned, for example, this power posterior method. And often, whatever method you were using to do inference for your standard posterior, it may not apply to the power posterior. But here, we're not messing with the posterior per se, and so you can just use MCMC or Laplace approximation or whatever you were doing. We can parallelize across B, right, just like with the bootstrap. So if we have sort of a cluster, we can go and have different nodes compute different posteriors conditioned on each bootstrap data set. And another nice thing is, so in the original sort of bootstrapping setting, we needed B to be really, really big, right? Because every bootstrap data set only gave us this point estimate. But now, every bootstrap data set gives us a full distribution. And so it just turns out that even taking B to be 50 or 100 empirically sort of stabilizes things. And that's sort of enough to get this full bagged posterior distribution. So it might be expensive to compute this pi of theta given a bootstrap data set, but B at least is sort of moderately large, and we can do it in parallel. Okay. And finally, we expect that we're going to get some of the nice finite sample regularization effects of using Bayesian inference from doing this, right? And again, sort of from a modeling perspective, we can think about modeling in the Bayesian framework. Okay. So that, yeah.
Can you give a couple of intuitions? What are the parameters that controls the extra width in the back posterior?
Yes. I will try to do that in just a couple slides. So first, I just want to give one more example. So I showed you this insurance example, but in a sense, that's like n equals 1 because I just showed you that I got better predictions for this one quantity, right? This sort of future claims amount. But that was sort of just, maybe we got lucky, right? So to get a lot more examples, we're going to use some synthetic data. In particular, we'll consider a Gaussian linear model with conjugate priors. And then we're going to consider different data generating distributions p sub true that we'll control, because this is all going to be synthetic data, simulated data. And we can either make the data generating distribution correct, so it'll be well specified, or we can make it misspecified, and we can just see what happens. And so I'm going to call theta opt sort of the optimal parameter that in some sense is closest to p true. I'm not going to formally define what that means. But you think of just theta opt as sort of the best parameter I can choose for predicting this data if within the model class that I'm assuming. And our performance metric is going to be to look at what is the posterior density that's assigned to this optimal parameter, right? So sort of in the limit of infinite data, this is the parameter that I would concentrate around. And I just want to see is the BayesBag posterior, or the bagged posterior, pi bb, assigning more density to this value, or is the standard posterior, okay? So I'm just looking at the difference between these. So if this is positive, that means BayesBag is doing better. If it's negative, then Bayes is doing better. And so here are the results. So again, bigger is better for the bag posterior. And so the different colors here just represent different data generating distributions. The first three are where the model is correct, just in sort of different parameter settings. And then the last one is when the model is incorrect. But what you can see is that in every case, actually, even in the well-specified case, because remember, even when the data is technically well-specified, you still have this prior, right? And that prior can bias you in various ways. And so what we can see is that even in these well-specified cases, for most of these data sets that I've generated, BayesBag is doing better. And when the model is incorrect, actually a lot of the time BayesBag is doing a lot better. Okay, so this is just nice because now I've been able to generate, for each of these settings, 50 data sets, so now I have a lot more evidence that this is actually working well. Okay. So that's sort of the method and some examples of how it works. But again, these are just sort of examples that I cherry-picked. How do we have any confidence that when you go and apply it to your problem, that this is still going to work well? So now I want to get to some intuition for what's going on and why we think that BayesBag is a good general solution. So, and the way we're going to think about this is in terms of sort of how is BayesBag quantifying our uncertainty, right? So first we'll think about bootstrap again. And so the bootstrap variance, right, is just the variance of the point estimate that we're getting as we change our bootstrap data set, right? So here's sort of the randomness is coming from the fact that we're resampling these bootstrap data sets. And so that creates some variance, right, some uncertainty. And so this is basically all about sampling uncertainty, right? It's about uncertainty about our data set, okay? Now let's consider the posterior. So I'm just using this sort of curly theta to denote something that's distributed according to the posterior. So the posterior variance, right, is just the variance of this this random variable. And here, this is going to be this is a kind of a model-based uncertainty in the sense that now our data is fixed. We're not changing our data at all. All the uncertainty is coming from essentially the fact that we don't actually know for sure what data is, but it's all sort of within the model itself. The data is fixed, okay? So here, we're changing our data. Here, data is fixed. So what happens with the BayesBag posterior? Okay, so now this var theta BB is indicating a sample from the BayesBag posterior. And now we want to write down what the bagged posterior variance is, okay? So it's going to have two terms. And we'll take them one at a time. This looks a little scary, but I promise it's not. So the first is the expected posterior variance. What do I mean by that? So this term, so here and here, right, this blue part, this is just the variance conditioned on a single data set, okay? So this is, again, model-based uncertainty. The data set is fixed, and then the variance is all because of this sort of the modeling uncertainty. And then we're just taking an expectation, so that's sort of just averaging over these variances. So, but all the sort of uncertainty is coming from the model-based part. On the other hand, the second term is the variance of the posterior mean, okay? And so now, so we have this expectation of our theta. So this is just the posterior mean given this bootstrap data set, okay? So this is, again, just a point estimate in the same way that we had this point estimate for the bootstrap variance. And so that means that this term is all about the sampling uncertainty. So in other words, our BayesBag posterior variance has both this model-based uncertainty term, like what we got from doing standard Bayesian inference, and also this sampling-based uncertainty, where, because of our uncertainty about the data set itself, okay? And it's the second term that's going to let us deal with the misspecification in the model, right? This part isn't going to be sensitive to misspecification, but this green part will be. Does this maybe help answer your question?
Yes, but how do they depend on the size of the bootstrap?
Yeah, so I don't have any details on that, but basically, yeah, so the way I wrote it down basically was you have this bootstrap data set, right? There's no reason that the bootstrap data set has to be the same size as your original data set. You could make it different. And that's basically just going to result in a rescaling of both of these terms by the ratio of the original data set to the bootstrap data set, roughly speaking, right? And so, yeah, I'm not going to get into that, but we do have some sort of methodology for figuring out how to choose that bootstrap data set size. But basically a reasonable default and sort of a conservative default is to just choose the bootstrap data set size to be equal to your original data set size. It's a good question. Okay.
Another question. Does it make sense to think of the bootstrap as this P of X that we often omit in Bayesian inference, so the probability of data independent of everything else?
No, it's a little bit different. Yeah, it's a little bit different because the bootstrap is, because that still doesn't sort of say anything about your uncertainty about the data set. That's just the marginal likelihood, basically, right? So that's just sort of a normalizing constant that you get. But again, it's still sort of a model intrinsic quantity, right? Whereas the bootstrap is sort of model independent. It's sort of this non-parametric quantity. Yeah, so it's still a little bit different. Okay. So just to summarize the previous slide, and then we'll sort of get to what the methodological implications of that slide are, is so we have the posterior variance, which is basically equal to this model-based uncertainty. And then we have the bootstrap variance, which is the sampling-based uncertainty. And finally, we have the BayesBag variance, which is the sum of the model-based and the sampling-based uncertainties. We get both simultaneously, okay? And so here, this is this mean example from before. What you can see is that in general, what we expect is that the bagged posterior is going to have greater variance than either the bootstrap or the standard posterior. So in general, it's not always true, but in general, so we kind of expect to happen. And then there's no strict ordering between the variance of the bootstrap distribution and the standard posterior. Okay, so turns out that when the model is correct, right, so when the model is well specified, essentially the model-based uncertainty and the sampling-based uncertainty are equal to each other, okay? They both correctly quantify our uncertainty about this sort of the optimal parameter. So yeah, so both the posterior and bootstrap variances are correct, essentially. But what that means then is that the BayesBag variance is going to be essentially double counting our true uncertainty because we're summing the model-based and the sampling-based uncertainty. So in the case that the model is well specified, the back posterior is going to be conservative. Okay. Now you can fix this. Since I've mentioned, I'll just say, essentially, if you take the bootstrap dataset size to be twice the original dataset size, then that will divide each of those terms in half, and you'll get the right amount of uncertainty. But the case that we're really worried about here, right, is when the model is not well specified, right? And when the model is incorrect, we're particularly worried that our model-based uncertainty might be substantially less than the sampling-based uncertainty. And that's essentially what we saw in the insurance example. Yeah.
I wonder if you could just explain a little bit more about the model-based versus sampling-based uncertainty, because my understanding was that they were variances just of different things. Right, so I thought that one was the variance of an estimator, and one was the variance to the true, the posterior variance to the true.
Can you clarify the question? So
I'm just confused because I thought that the model-based uncertainty was the variance of the true value conditional on the data.
It's the variance. The model-based is just the posterior. It's basically just the posterior variance, conditioned on a single fixed data set.
Yeah. So it's the variance of the true parameter.
It's sort of the variance of our. It's sort of quantifying our uncertainty about what the true parameter is. Essentially, it's sort of intrinsically. You can think of it as being conditioned essentially on the model being correct as well as on the particular data set that we observed. Yeah.
Yeah. So, but it's kind of the variance of a different thing than the variance of the estimator.
I guess you can think of them as being quantifying like different types of uncertainty if you want. But we can see that they both I don't want to go back, but we can see that they both can kind of arise through this identity in the bagged posterior variance, right? They both arise as just this decomposition. So in some sense, they're both sort of they're different types of variances, but they can still kind of arise from a single thing.
Why do you want them to be the same?
Why do you want what to be the same?
Those two values.
Oh, I'm not saying you necessarily. So what we're really interested in here is what we don't want to happen is to be really certain that the true parameter is x, right? When it's really like x plus 20 or something. Because then if we get more data or then we observe new data, our predictions we're going to be really overconfident, right? Like that's what we saw in this insurance example where because the model is misspecified, right? We are overly confident, and then we're not going to make good predictions or good decisions about future data, essentially. Yeah, or just it's relevant both from the prediction perspective. It's also relevant, right, from more scientific parameter inference perspective, right? We might just be overconfident that a coefficient is positive, when actually because the model is misspecified, it's actually maybe it's not, right?
So I guess my question is really what is the sampling-based uncertainty? Are you assuming there's a particular estimator being plugged in there?
Yeah. Yeah, exactly. So basically, in the case of BayesBag, it's plugged. Yeah. So in BayesBag, right, you specifically have the point estimate being the posterior mean, versus Bootstrap. You can sort of do whatever you want, but the typical thing is like a maximum likelihood estimate.
So maybe there are some estimators, you could pick a really bad estimator, for example, that just looked at the first data point.
Yeah.
Sampling-based uncertainty would always be really large.
Yes.
And maybe there's some estimators. You're saying there's in particular, if you choose the.
So if we kind of want to think about it more rigorously, there's efficient estimators basically, right? So and it turns out, for example, in a lot of reasonable models, basically the MLE and the mean are going to be asymptotically equal, or essentially equal to each other, right? They're basically the same.
Do you want things that are consistent and efficient?
Yeah, exactly. Yeah. So there's some sort of like asymptotic theory that we can use to make all of these sort of, again, I was trying to kind of keep things high level and not get into the asymptotics, which we have in the paper. But yeah, and sort of try to go with intuition more than the rigorous asymptotics. Yeah. But that's sort of the way to think about it. Okay, yeah. So, right, so the situation we're really worried about is this model incorrect setting where maybe our model-based uncertainty is way too small, and then our posterior variance is far too small, and then we make these bad predictions. But in that case, BayesBag is not going to have this problem because it has the sampling-based uncertainty term too. Okay. So the other cool thing that we can do with this is we can actually just try to diagnose when the model is misspecified, right? Because one thing you might want to do as a model builder is say, okay, well, sort of going in, I'm going to do my best to write down a model that I think is good, and then I'm going to get some data, and I'd like to check, like, is that model actually any good, right? A lot of scientific, settings, we just don't understand a system very well, so you sort of do your best first pass, then you get the data. And so it's nice to be able to do what we call model criticism and actually get some insight into whether the model is correct or not. And so we can use BayesBag to do that. And essentially, we can use these two formulas that I've rewritten again to compute what we call the mismatch index. I'm not going to formally define it, but it's sort of this very nice quantity on this interpretable scale. So it runs between -1 and 1. And basically, if it's about 0, that indicates that there's no disagreement between the data and the model. So that sort of suggests that there isn't any misspecification. If it's significantly greater than 0, this suggests that the posterior is overconfident. And if it's less than 0, it suggests that the posterior is underconfident, right? Which can also happen, right? You can in theory run into the problem where your posterior has lots of uncertainty, but actually you should be very certain. And so, for example, in this future claims insurance example, the mismatch index is approximately 1. And so it correctly detects the fact that there's significant misspecification in this model. So this lets us do model criticism and indicate when we might want to actually try to improve the model. Again, that's not always possible, so it's nice to have this robustness built in. But if it's feasible, maybe you want to try to improve the model. Okay. And I guess the last point is that this mismatch index can also indicate potential problems with your prior as well. Okay, so to summarize, sort of what does BayesBag look like in practice? What would we actually do? So you could imagine the following workflow, which is we start by computing the standard posterior, pi of theta given y. So for example, maybe we run MCMC and get some approximate samples. Then we're going to compute the bag posterior for, say, b equals 50 bootstrap data sets. So that means we'll say use, again, MCMC to get these approximate samples from the posterior conditioned from each of these bootstrap data sets. And then if essentially if a Gaussian approximation to the standard and bag posteriors is somewhat decent, under those conditions, we can use this mismatch index. We can compute it, and say if it's fairly large, then we might consider refining the model and then returning to the beginning. And otherwise, you can just output this bag posterior that you computed in step 2 as a robust alternative to the standard posterior. Okay, any questions on that? Cool. Okay, so for the final part of the talk, I want to turn to another important type of inference problem, which is model selection. So in model selection, we now imagine that we have our data, and our goal is to select between a finite or a countable set of models, which I'll denote by M1, M2, et cetera. That's kind of the flavor, actually, that Will's example had, right, in the linear regression example, where you're trying to figure out, like, what degree polynomial should you choose. So these are sort of different models you're trying to select between. The example that I'll get into in more detail soon is from systematics. And that's where our goal is to learn about the evolutionary history of, say, a set of species, like whales, maybe. But it could also be, say, the evolutionary history of a tumor or something like that as well. And so what does this history look like? Well, we have these whale species, say the fin, the blue, the gray, and the minke whale. And we just want to know how closely related they are to each other. So what are the shared common ancestors? Sort of in what order did they occur? And then sort of how much, the length of these lines indicates basically how much evolution there was sort of to separate them. Okay? And there's lots of different possible trees that we could write down. And we want to figure out what the sort of correct evolutionary history is. So the Bayesian approach is going to be to try to infer the phylogenetic trees that are consistent with some observed species characteristics, right? So, these days that's usually genetic data of some kind, but it can also be physical features such as coloring or other things like that. And the problem is again going to be that implicit in using Bayesian model selection is the assumption that one of the models that we're choosing from is correct. And if that's not the case, things can go a little off the rails. So to get, so actually I'm going to start with a little bit of theory and then I'll give some examples. So let's just assume for simplicity that we only have two models, M1 and M2. So for example, two possible trees. Now, if these models explain the data generating distribution equally well, right? So they're both sort of equally good explanations for the data. They're both wrong, right? We're working in this misspecified setting. What we'd hope would happen is that with enough data, the posterior would assign equal probability to both of these models, right? Neither one is better than the other. Okay? That's what we might hope would happen. But it turns out that's not the case. So if we assume the models are equally good, then in the large data limit, for the standard posterior, what happens is that the posterior probability assigned to the first model is going to be 0 or 1 with equal probability. In other words, we're going to be completely confident that model 1 is correct or completely confident that model 1 is incorrect, even though model 2 is just as good as model 1. So what might this look like? Well, here I'm showing you these different realizations of our data set. Or you can also think about this as our data set with the size increasing, say like doubling each time. And what will happen in either of these settings is that you're going to flip back between being totally convinced that model 1 is the right one and that it's the wrong one. So probabilities will go back and forth between being 0 and 1. Okay? So we're assigning all of our posterior mass to a single arbitrary model, even though they're both equally good. The bag posterior, on the other hand, it will assign a uniform probability to model 1 instead. Okay? So it might look like this, where here it's sort of low, but still non-zero. Here it's getting up towards 1, but again, not quite 1. Here it's actually still pretty high. And it'll sort of bounce back and forth, but it's never going to be completely convinced that one model is correct or the other is correct. Right? So it's going to more evenly distribute the mass between these two models. Okay? So to get a little more intuition for this, I'll start with an illustration in a very simple and somewhat silly scenario where our two models are either that our data is generated from a normal with mean -1 or from a normal with mean 1. All right? But in fact, our data is going to be generated from a normal with mean 0. Okay? So here's what those three distributions look like, right? And it's sort of obvious just by symmetry that model 1 and model 2, neither is correct, but they're both sort of equally bad explanations for the mean 0 data. Okay? So again, what you'd hope would happen is that it would just assign equal probability to both. So what we're going to do is we're going to generate a bunch of data sets of size 1,000. Again, because this is our true distribution, all these observations will be normal 0, 1. And I promise these are the first 3 data sets that I drew, and this is what I got in the first case. So here's the data set. And the posterior probability that assigned to model 1 was 1. But BayesBag assigned 0.82. Here's a second data set I drew. Now it's completely convinced that model 1 is incorrect. So it's basically probability 0, very close to 0. But BayesBag, on the other hand, is still pretty unsure about which one is correct. And then finally, on the third data set, we're back to believing that model 1 is definitely the correct one. All right? This is kind of wonky. And why should we be really worried about this? Well, let's go back to this phylogenetic inference example. So now our goal is going to be to infer the phylogeny, right? This phylogenetic tree of 13 whale species based on their mitochondrial coding DNA. So here I've shown our 4 friends from before, but there'd be more for the other whales, and we have, we just have these sequences of DNA. And so what we're going to imagine to kind of reproduce the setting that we had before is we'll consider, okay, what happens if we just look at the first half of each sequence? What happens if we just look at the second half of the sequence? Or what happens if we look at all of the data, right? So you can imagine these are scenarios either where you get 2 different data sets, right? And you want to see, like, are these consistent with each other? Or I start and I get 1/2 of the data set, I do inference, and then I get more data. Do my beliefs completely change, right? That's what we're kind of worried about, right? So here's what, maybe, you look at the first half of the data, you think that these are sort of the 3 most plausible trees, and then when you get all the data, now these 3 ones look the most plausible, and that's fine, right? We don't expect our inferences to be exactly the same. We got more data, but they shouldn't be completely different either. So basically what we're going to do is we're going to compute the posterior tree probabilities based either on all the data or the first half or the second half. And then we'll look at the overlap of these sort of high probability regions, okay? So we'll just sort of say, okay, what are the trees that are in like the 99% high probability region? And compare sort of how much probability mass there's that's overlapping. So just to be concrete, so imagine that we're comparing all the data to the first half, like here, and we just have, say, 4 trees. So maybe the posterior distribution over these trees for all the data is given by like 0.5, 0, 0.19, and 0.3. And so the sum of these, because we're looking at a 99% high probability region, is going to be 0.99, okay? And then here are the results maybe that we get from just looking at the first half of the data. And so some of them will be, so here, okay, we actually have some probability mass on tree 2, which we didn't have any before, but we don't have any on tree 4. And again, the sum of these is going to be 0.99. And the overlap is just the minimum of these 2 values, right? So it'll be 0.2 here, 0, 0.19, and 0. And again, and if we sum these up, so our total overlap is 0.39, okay? We sort of expect that there's going to be at least some overlap between these two posteriors, because they're based, at least in part, in the same data. Okay, and if we get 0 overlap, this basically means that we have a contradiction, right? We're completely convinced that one set of trees was true, and then we got a little more data, and now we're completely convinced a different set of trees are the true ones. So let's see what happens. Well, it turns out that for some evolutionary models, we get basically little to no overlap. So okay, what do I mean by evolutionary models here? So we talked about we're doing model selection, right? And that's basically about selecting the tree, right? The phylogenetic history. But we have a bunch of characteristics of our species, and one thing we have to specify is like how are those evolving over time? Basically, what's our evolutionary model? And that's sort of uniform across all the different trees. So you have to select that too. And so here I'm just looking at different evolutionary models and asking sort of what are the inferences I get about the trees for these different evolutionary models. And what you can see is that there's a lot where we're sort of in this danger zone where there's almost no overlap or zero overlap between either if we look at the first half versus the second half, or all versus the first half of the data. And in fact, for these two models, there's exactly no overlap between them. So we're getting these contradictory inferences. And this is a well-known problem in this community. Okay, there's a whole series of papers exploring this fact and worrying about it, right? Because they're trying to use Bayesian model selection, but it's completely unstable and it's not reproducible, right? They just really can't trust the inferences that they're getting from it. And you can also get the same problem if instead of changing the data set, you change your evolutionary model. And again, like these models are all misspecified. We're not sure which one is right. So actually, like this evolutionary model is based on using the amino acid sequence, versus here we're using the actual DNA sequence. And if you change between those, you can get completely different answers, right? And so this is like pretty disturbing to these guys. And so, and they really didn't seem to have a great fix. Usually the thing that people seem to do is they like compute it with sort of in every way they can imagine and just report out all the results, right? Which is not very satisfying. But what happens when we use the BayesBag posterior? Well, our theory suggests that we should get much more stable results. And that's exactly what happens. So now we can see that most of these overlap numbers are much larger, right? Much more significant. And there's very few that are really, really low, indicating these contradictions. And in fact, even this guy who looks pretty close to zero is in fact non-zero. So we no longer have any zero overlaps where we're getting completely contradictory inferences. Okay, so just to close out, we've shown that BayesBag has these really nice, provably good statistical robustness properties, right? Better quantification of our uncertainty in the case of parameter inference, and more stable inferences in the case of model selection. Demonstrated empirically that we also get superior predictive performance compared to standard Bayesian inference. And then next, it's also, it's very easy to use and it's widely applicable, right? There's no sort of new computational machinery that you have to come up with to do this. You just compute a bunch of posteriors and average over them. And finally, sort of what's the takeaway? Well, we're combining the flexible modeling features of Bayesian inference with the distributional robustness of frequentist methods, and in particular of the bootstrap. I think there's a lot of exciting directions for future work here. In addition to just having other people apply this and see how it works on their data. So if you're interested in doing that, definitely let me know. But in addition to that, thinking about time series and other structured data where it's a little trickier to apply the bootstrap. Sort of the way I framed it here, basically all your observations basically have to be exchangeable, or you can think about them as being independent of each other. But if you have some more structured data like time series or spatial data or something like that, you have to be more careful. And then we still have to speed up computation. Computing 50 posteriors can be time consuming, especially if you have a lot of data or it's a complicated model. So we'd like to speed up computation. And then finally, I'll just say that this will be on the archive very, very soon, I hope by early next week. And so if you would like a heads up for when that actually happens, feel free to drop me an email and I will be sure to let you know. Thanks very much.